Okay, I have started the recording. I also share my screen. Yeah. I hope my screen is visible. Yeah, we'll wait for maybe 2 more minutes and we'll start at 6:1. Okay, so we'll get started. Um, so, Debanuj, did you attend last class? Can you hit a like if you attended last class? Okay, then. So I assume that you are familiar with the material that we covered in last class. So basically, I'll assume that given a system of linear equations, you know how to convert this into AX equal to B format. You'll know how to convert this system of linear AX equals B format. So this is the precursor to today's lecture. I assume that you are familiar with this. From this, we'll get started to some important concept called row reduced echelon form. Row reduced echelon form. So today's class, we will see what does it mean to reduce a matrix A to RREF. By RREF, I mean row reduced echelon form. And what is the advantage of reducing a matrix to RREF, right? So the context is still going to be same. The end goal is to solve system of linear equations, meaning let's say I give you four equations with four unknowns. The task is to find assignments to unknowns in the equations. That is, you need to assign values to x1, x2, x3, x4 such that all four equations are satisfied. Right. Now, to recap what we saw in last class, we saw that this four equations can be represented in Ax equal to B format. Once you do so, one familiar method to find the correct assignment to x is by inverting A. That is, you can find x equals A inverse B, right? And in last class we saw why this inverse based solution is not appreciable. We saw some cases where like A inverse may not exist, and we saw some computational reasons also, right? And in general, if you are using some standard libraries to find solutions to system of linear equations, nobody will do this, right? So with this inspiration, we'll see one elegant way of obtaining the solution x, right? So now to understand how to obtain this solution using more in a more smarter way, we need to understand what is RREF. So today's class we will see how to convert A to RREF, and in next class we will see how to use RREF to obtain X. So that is going to be the plan, right? Yeah. So first let me begin with introducing what is RREF to you. So RREF is a matrix of the form. It is a upper triangular matrix. Now, what do we mean by upper triangular matrix? Now, given a matrix A, if you consider the leading diagonal, all the leading diagonal entries should be 1. All the leading diagonals entries should be 1, and the entries below the leading diagonal should be all zeros. These are all entries should be zeros, right? And entries above the leading diagonal can be anything that is arbitrary. Maybe let me not use x. This can be any real number, right? I hope the structure of the RREF is clear to you. More formally, we call RREF as a upper triangular matrix. Why do we call this as upper triangular? Because you have entries, non-zero entries, only above the leading diagonal of the matrix. Now you may ask, if A is rectangular, so here I told you I am showing A which is a square matrix. That is why leading diagonal, if you start from top left corner, it is spanning all the way to bottom right corner. Right? Now you may ask, what if A is rectangular? Rectangular, right? For example, A may be M cross N, right? Then how will the structure look like? So for instance, I'm showing a matrix A whose height is less compared to width of the matrix. Now in this case, if I were to draw the leading diagonal, the diagonal will end somewhere here, right? Then in such a matrix, we call this rectangular matrix as RREF when all the entries along the diagonal are 1, all the entries along the diagonal are 1, all the entries below the leading diagonal should be zeros, and entries to the right of the leading diagonal can be anything that is arbitrary, right? Now in this class, we'll see an algorithm or a procedure to convert any given matrix A into this format, right? Now, I hope this is clear to you. What is the upper triangular matrix, and what does it mean to convert a matrix to row reduced echelon form? Yeah. So now, so before even like starting, um, I would like to motivate the procedure of obtaining RREF intuitively, right? So one thing is so always remember that the exercise that we do in this class, last class, and the following class, I mean the next class, is in context of obtaining solutions to system of linear equations. This should always run at the back of your mind, right? Now let's try to mimic what all will you do, what all are legal operations in obtaining solutions to given set of equations. What are the legal operations? For instance, let me take a easy system. Yeah, let me go to next. So here, what we're trying to like argue are legal operations in obtaining solutions to system of linear equations. Now let's say I give you a system, right? Sorry, yeah. Let's say I give you a system x1 plus x2 equals 3 and minus x1 plus x2 equals 1. Now, can somebody tell me what will you do to obtain assignment to x1, x2? Solve it using UC. I mean, usually how you will solve. How will you obtain solution to x1, x2? I think this exercise we did in last class. So let me go ahead and do it. First thing you will do is you will make R2 equals R2 plus R1. Right? When you do R2 equals R2 plus R1, you will get 0 times x1 plus 2 times x2 equals 4. This will give you that x2 equals 2. Right? Now, what is one operation that is legal? You can take a row, you can take a row R2, and to that row, you can add or subtract one more row. You can add or subtract a scalar time multiples of other row. Right? So, what I'm saying is one legal operation number one is called as linear combination. The technical term is called linear combination. So here what I do, you will take some row Ri, and to this Ri, you will assign Ri plus some alpha times Rj, where alpha is a real number. Right? So one thing you notice here, if you are taking a row, Ri, let's stick to this notation that if you take Ri, the scalar multiple will be attached only to Rj. Why I do this will be clear to you later. So going forward in the class, we will see something called LU decomposition. LU decomposition. Now in LU decomposition, it turns out that if you write equations in this format, obtaining LU decomposition is relatively simpler, right? In pursuit of solving LU decomposition few classes later, I would like to stick to this notation, where if you are adding two rows, the scalar corresponding to that row can be will always be attached to the other row. Okay. Now, is this a this is not a problem. For example, let's say you are intending to do r, let's say r1 equals 2 times r1 plus r2, right? This equation also you can represent in this format. You can take this scalar and attach it to the other row. Okay. Now, this is the first kind of operation. I think you're all convinced that this operation is a legal operation. Now, I gave you the system of equation. What is forcing us to write uh, the first equation in the first row and second equation in the second row? What is forcing us to write? I can swap these rows, right? So what I mean is, I could have solved this system instead, right? I could have solved minus x1 plus x2 equals 1 and x1 plus x2 equals 3. I could have solved this, right? Still, I will get the same solution. For example, when you do R2 equals R2 plus R1, you will again get 2 times x2 equals 4, which is x2 equals 2. This is the same solution that you obtained earlier, right? And this gives us light that swapping of equations is also a legal operation, right? Second operation, technical term is called as permutation. What do I mean by permutation? Meaning you obtain the matrix format of the system of linear equations. Let's assume the matrix is, let's say, a x equals b. Now this operation says that you can permute any rows of the matrix arbitrarily, right? For instance, let's say the matrix A is, let's say, a1 dot. By dot I mean, so this first row, and the column spans this way. So I have a2, a3 up till an into x equals b1 till bn, right? um, Now what this is saying is you can permute the rows of the matrix, but mind you that when you permute rows of a matrix, you should also permute rows of b matrix, but you should not permute rows of x. Should not permute rows of x. Can somebody guess already why we should not permute rows of x? Okay, so let me give you the answer. So, for example, if you take this system, right, the system of equations that I have given you here, this is the matrix representation of the system. You can write it as minus 1, 1, and 1, 1, x1, x2 equals um, 1 comma 3, right? B is 1 comma 3, right? Yeah, B is 1 comma 3. Now, what I'm saying is you can permute rows of the matrix, but you are not allowed to permute rows of x, right? So this is A, this is x, and this is B. In permutation, you can permute rows of A. Rows of A is valid. You can permute rows of B. Sorry, not can, you should permute rows of B in the same order that you permute A, but you cannot permute rows of X. You should not permute. Now let's see what will happen if you permute rows of X also. So let's assume the order is 1, 2. That is, you have first row and you have second row here. Now if you permute the rows so that you get the order as 2 comma 1, then what will happen? Matrix A will become 1, 1, minus 1, 1. Let's say you permute x. Then if you permute x, what will happen? X2, x1 will become x2 and x2 will become x1 equals 1, 3. Right? Now do you see what's the problem when I permute x? Can somebody tell me what's the issue here? Hello, hello. Hi, sorry, I did not realize my internet was off. Yeah, I kept talking and yeah, I did not realize that. Yeah, so can people hear me now? Loud is it or audible? Okay, okay, yeah. So what I was saying is, I am in hostel connected to Wi-Fi. While I was talking, I think some point in time the internet went off. I did not realize and I kept talking. So until when was my voice audible to you guys? So until when did you hear me? Were you able to hear me? Hello, Vikrant, am I audible? Oh, you just joined. Okay. So then, okay. So okay, maybe for the benefit of class, I will kind of reiterate what I have been saying. So what I said was, so in this class, we will see an elegant way to approach solution to a system of linear equations, right? Now here we are given an example with four equations and four unknowns. Now, last class we saw how to represent the system of linear equation in a matrix format. What we did, we put the coefficients of the unknowns in the matrix A in the order that we have in X, right? So we fix the order in X, and in that order we fill the coefficients in the matrix A. Then we take all the constants to the right hand side and then fill the matrix B. I hope you recall, this is what we did in the last class. And last class we saw that typically we can obtain solution to X by A inverse B. And we saw some drawbacks last year. Sorry, last class. Why is A inverse B not appreciable solution? Right? Now, last class we saw, okay, this is not a good way to obtain solution. Now we are going to see an elegant way to obtain solution. That is called as that is obtained when you reduce A to something called row reduced echelon form. So I started the class by saying what is row reduced echelon form. So here we consider an example where we are given a matrix A that is square, that is n cross n. Given a n cross n matrix, RREF, by RREF I mean row reduced echelon form. So RREF has this structure. So first what you do is to draw a leading diagonal. That is from left to right, you draw the diagonal. Now we say that matrix A is RREF if the entries along the leading diagonal are ones. Entries along the leading diagonal. Yeah. Oh, yeah, 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 yeah. I did not share the screen. Yeah. So, sorry about this. Can you see it now? Okay. Sorry for the mess up. Yeah. Okay. So were people able to follow me by what I mean by RREF form? So we call a matrix A in RREF when the entries along the leading diagonals are one, entries below the leading diagonal is zero, and above the leading diagonal can be any real number. Okay. So this is the story when A is a square matrix. Now, what will happen if A is a rectangular matrix? If A is a rectangular matrix, the leading diagonal will not span all the way till bottom right corner of the matrix, right? If you draw the leading diagonal, it may stop somewhere in the middle, right? But still, our definition of RREF is consistent in the sense the entries along the leading diagonal should be 1, entries below the leading diagonal should be 0, entries to the right of leading diagonal should be any arbitrary real number, which means this portion, the portion I'm sharing in there in purple, this entire portion can be any arbitrary real number. But the portion that I'm shading in red here, this should be all zeros. Okay, so I hope the structure of RREF is clear, right? Now, next, next we were discussing how to convert a given matrix into a row reduced echelon form, meaning how to convert a given arbitrary matrix into into a form where leading diagonals have ones, and basically I think you get the point, right? Now, further I told that technical term to this matrix is called upper triangular matrix. Upper triangular matrix. What do I mean by upper triangular matrix? um, the entries only above the diagonal, only above the I mean entries on or above the diagonal should be non-zero, right? Or rather, entries below the leading diagonal should be all zeros. That is when you call a matrix to be upper triangular matrix, right? Now, I said, like I could have given you the procedure to obtain A to RREF, right? The procedure is in fact very simple, but I would not like to give you the formula to obtain the RREF matrix. Rather, I would like to motivate the steps of RREF by drawing inspiration from what you would do in if I give you a question and ask you to solve it in paper, what will you do to achieve attain a solution of system, right? You'll do some steps. Now those steps we will formalize, and from those steps we will inspire the procedure to obtain to procedure to reduce a matrix to RREF, right? Now for that we need something called legal operations. I call this as legal operations. Now what are legal operations? Now I give a system of linear equations and ask you to solve it in paper. Now whatever you do to obtain the right solution is a legal operation, right? Now for example, take this system: x1 plus x2 equals 3 minus x1 plus x2 equals 1. Now to obtain solution to this system, one possible step that you will do is you will add r1 to r2. Why will you do that? Because when you do so, one variable gets eliminated, right? Because x1 minus x1 is 0, this variable will get eliminated. As a result, you will get one equation with one unknown, and we know how to solve one equation with one unknown. So when you do r1 r2 plus r1, you get 2x2 equals 4. From this you get x2 equals 2, right? Now from this operation that you do on paper, I am formalizing linear combination. So sorry, yeah, a linear combination is any operation of the form Ri equals Ri plus alpha times Rj. Alpha is a scalar. By scalar I mean a real number, right? You can do any such operation on a matrix, and that is a legal operation. Why? Because in obtaining solution, this x2 equals 2 and x1 equal to something, you can add any number of rows with any arbitrary scalar. Of course, alpha, yeah, alpha can be 0 also. If alpha is 0, basically Ri will be equal to Ri, right? I hope this linear combination is clear. Is there any doubt with the linear combination operation? Later we will see how to apply this linear combination in a matrix format. Okay, I assume this is clear. Now, one may wonder, why am I saying that Ri equals alpha, Ri plus alpha Rj? Why can't I simply instead? Why can't I do Ri equals some alpha times Ri plus Rj? So this is also a legal operation. This is also a legal operation only. Okay, but I request you not to do this. Why? Because in future we will see something called LU decomposition, and LU decomposition, if you restrict yourself to equations of this format, Ri plus alpha times Rj, it turns out that obtaining solution to LU decomposition is simpler, right? In view of the future class, I only consider operations of the type Ri equals Ri plus alpha times Rj, right? Now second operation we are seeing is permutation. So was I still audible when I introduce permutation, or should I start permutation from the beginning? Okay, okay, sure, 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 yeah. Okay, I'll start permutation from beginning. So now, um, permutation, right? So now you are given a system of linear equations. So let me take this system: minus one 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 x one x two one three, right? Minus one 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 x one x two equals 1 3. This is a system I have. What are the equations corresponding to the system? Minus x1 plus x2 equals 1, Yes, and x1 plus x2 equals 3, right? Now, will the solution I obtain be any different if I permute the rows? Meaning, if I consider system in this order, x1 plus x2 equals 3 minus x1 plus x2 equals 1. If I consider this system where the rows are interchanged, will the solution that I obtain be any different? No, right? So in this system also, let's say I do R2 equals R2 plus R1, then I'll get 0 times x1 plus 2x2 equals 4 and x2 equals 2. This is consistent with what you obtained earlier, right? So that is why um, permutation is also a legal operation in obtaining solution to system of linear equations. Here I would like to stress one point that yeah. So let's assume this to be the original matrix, that is A x equals B, Ax equal to B. Now if you swap the rows 1 and 2 in this system, then you should not swap x. Meaning after swapping, your matrix will be 1 1 minus 1 1. A will get swapped, B will also get swapped 3 1, but you should not swap x. X will still be x1 x2. Yeah, x will the matrix, the vector x will still be x1 x2. Do you see why? Can somebody answer why I should not swap x1 x2? So in this matrix actually, um, r1 and r2 are interchanged, and in this matrix again r1 and r2 are interchanged. What will happen? Let's say I make this x2 x1. Can somebody find the fault? Can somebody say me what is wrong in this? Am I still there, or am I audible? Yeah, yeah. Okay. So, is somebody able to fault the? I mean, notice a fault in changing. I mean, permitting X also. Mhm. Exactly. So, how is the equation changed? Then, if I multiply a into x, what will happen? I'll get x2 plus x1 equals to 1. Sorry, x2 plus x1 equal to 3 minus x2 plus x1 equals 1. Now, if you solve this system in a situation where you have swapped rows of x also, then you will get 2x1 equals 4. From this, you will get x1 equal to 2, x1 equal to 2, right? But in the original system, x2 equals 2, not x1 equals 2. Do you see the mistake? Yeah. So you should not swap rows of x. So, yeah, let me formalize this. So permutation is a legal operation, but your permutation should be only limited to A and B in same order. This is very important. Okay, you should permute in the same order. Now we have seen two operations. One is where I call the linear combination, other I call the permutation. Now third operation is a scalar multiplication. I think this is very simple. What do I mean by scalar multiplication? Again, let me take the system. Minus x1 plus x2 equals 1, x1 plus x2 equals 3. Right? Now I can multiply both the equations by 2. For example, let's say I multiply by 2, this I multiply by 3. Then what will happen? The resultant system will be minus 2x1 plus 2x2 equals 1, 3x1 plus x 3x2 equals 9. Right? Now I can do now to obtain solution. What I can do, I'm beating around the bush, but maybe to make you understand, that this also legal operation. Let me go ahead and do that. Right? I can do R2 equals R R2 R2 plus plus 3 by 2 R1. Right? What will happen if I do that? I'll get 2x1 plus when I multiply by 3 by 2, I'll get 9 by 2 x2 equals 27 by 2. Right? Now I can add, add r1 and r2. Then what will happen? X1, this x1 will get cancelled. Then what I will get is 2 plus 9 by 2. What is 2 plus 9 by 2? 2 plus 9 by 2 will be 13 by 2. 13 by 2 x2 equals 20. Is it 27 or 26? Yeah, 27. Um, yeah, I think I'm making a mistake somewhere. No. Right, right, right. This should also be 2. This should also be 2. Then this will be 27 by 2. So 2 plus 27 by 2 will be 4. Oh, still it is wrong. I'm making mistake somewhere. I think I should get here 26 by 2 or something for x2 to be equal to 2. Yeah, let me just check it. So if I multiply this with 2, I'll get minus 2x1 plus 2x2 equals 2. When I multiply this with 3, I get 3x1 plus 3x2 equals 9. Now, then if I add these two together, uh, right, here is the mistake. 3x1 minus 2x1. Okay, I'm adding 3 by 2 r1. So when I add 3 by 2 r1, oh, yeah, yeah, yeah. The mistake is this should be 2 by 3 r1. Do you see the mistake? It should be 2 by 3 r1. Then this 3 and this 3 will get cancelled. I'll get 2 here, right? If I multiply 2 by 3 r1, basically I'll get 2x1 here, and this 3 and this 3 will get cancelled. Then I'll get 2x2. Then 2 by 3 will be this. This will be 6. Okay. So let me rewrite this. So what I'm doing, I'm multiplying R2 equals R2 plus, oh, 1 second. Sorry, I'm getting confused. Just 1 second. So R2 equals R2 plus, hmm, yeah, 3 by 2 is correct. 3 by 2 R1 and plus is correct. Yeah. So when I multiply R1 to 3 by 2, so this will be minus 3x1. So this will be 0 times x1, and 3 by 2 will be 3x2. This will be 6 times x2. Yeah, 6 times x2 equals, when I multiply 3 by 2, I get 12. Yeah, now I get the equation. So 6x2 will be equal to 12, then x2 will be equal to 2. Now do you see, I can multiply, equations with any arbitrary scalar, but that scalar should not be equal to 0. You should not multiply with a 0 scalar, but you can multiply with any positive or negative number. Still, the system of linear equation will be consistent. By consistent, I mean you get the same solution. Is it okay? Yeah. Now let us see. So basically, we have seen three operations. One is called linear combination. Second is called permutation, and third is called scalar multiplication. I'll show you that for any given matrix, these three operations are enough to convert any A, be it square or rectangular, to RREF. Right? Now let's take the matrix in the above system. Let's take a difficult example now. Let me bring this image. Yeah, let me copy this image down. Now let's consider the system of equations here. Let us consider system of equations here. Can somebody read out ax equal to b here? So okay, let me not start with ax equal to b. Last class we saw an augmented matrix, right? A comma b. Let me write down the augmented matrix for the system, right? Augmented matrix will be 1, 1, 2, minus 1, and let me augment b also. So this will be 1. Then for second equation, minus 2, minus 2, minus 3, 5, b will be 0. Third equation, 1, 1, 3, 2, b is 3. Last equation, 0, 0, 1, 3, b is 6. Right? Now remember the format of RREF. So let me draw the diagonal here. So diagonal is basically diagonal ends here, which means our target is to make the purple entries equal to 1 or 0. So basically, we'll try our best to make the entry as one. There may be some cases where you cannot you cannot really make an entry as one. In that case, you just give up and you make that entry 0. Okay, our target is to make the purple entries 1 and the red entries 0. And how will you make it? We'll make only using the three operations that we discussed so far. Right now, firstly, you see this is not an RREF. Why? Because yeah, okay. Now let me give you the procedure. So the way you will proceed the way you will adjust the entries in basically in this order. You will start with first column. You will try to make the first entry in the first column 1. All the entries below row 1 you will make 0. Once you are done with first column, then you will go to second column. In second column, as you are aware that any number in this entry is fine. So you will not bother about this entry. You will come to second entry of the second column. You will try to make this entry 1, right? If it so happens that you cannot really make this entry as 1, then you will try to make it 0, right? Once you make this second entry of second column 1 or 0, then you will make all the entries below the all the entries in the column 2 below the entry 2, this you will make it to 0. Then you will come to third column, you will make the entry 1 and the entries below the pivot entry, you will make it 0. Right now, this is a procedure we are going to follow. Right now, following this procedure, you see already that in the entry 1 of the first column, the condition is already satisfied. Right, because the condition is satisfied, let's go to the other entries below the first entry. Right, can somebody suggest operations can somebody suggest a right operation to make this entry 0? So now I want to make this minus 2 to 0. Can somebody suggest an operation? So remember that you can only use three operations. One is linear combination, other is permutation, third one is scalar multiplication. Anyone? Yeah, right. R2 equals, that's right. R2 equals 2 times R1 plus R2. So this is correct, but I request you to stick to the notation in this format. Ri should be equal to Ri plus alpha times Rj. Let's always follow this notation. Right. Again I'm repeating this only because to make LU decomposition easy later. Okay, so your equation is perfectly correct, but I would like to rearrange in this format. R2 equals R2 plus 2 times R1. Okay, once I do that, what will happen? I will obtain the matrix uh, 1, 1, 2, minus 1, again. So, yeah, 1, again 1 here. Now, when you multiply R2 equals R2 plus 2 R1, you will get 0. R2 plus 2 times R1 will be, this will be again 0. Then this will be minus 3 plus 4, right? Which will be 1. Uh, Please alert me if I am doing some calculation mistake. Then it will be 5 minus 2, which is 3. And this will be 0 plus 2, which is 2. And I'll simply copy over the remaining rows, which is 1, 1, 3, 2, 3, 1, 1, 3, 2, 3, and last row is 0, 0, 1, 3, 6. 0, 0, 1, 3, 6. Right? How did we obtain this matrix? We obtained by applying the operation R2 equals R2 plus 2 times R1. Right? Now, following our pseudocode, I mean, following our procedure, next we want to target this entry. We want to make this entry 0. Can somebody suggest an operation? Yeah, R3 equals R3 minus R1. Right? R3 minus R1, or to stick to this notation, I can write R3 equals R3 plus minus 1 times R1. Okay, so I always want the equation to be in this form. R3 Ri equals Ri plus some alpha times Rj. Okay, so here alpha equals minus 1. Now when you do that, let me update in the same matrix. So when I do R3 equals R3 minus R1, so this entry will become 0. This entry will become 0. This entry will again become 0. 3 minus 2 will be 2. 2 minus 2 plus 1 will be 3. 3 minus 1 will be 2. Right? Now we see that this entry already condition is satisfied. Right? Now what we can do is to proceed to the second entry of the second column. Because this first entry lies above the leading diagonal, this entry we don't care, whatever it is. Right? We'll come to second entry of second column. Now, here we see our expectation is that we need to make this entry equals 1. Right? But I find a 0 here. Now, can you suggest one of the three operations using which you can make this entry to 1? Is it possible to obtain a 1 here using the three operations that I told you earlier? Okay, let's try one by one. At this thing, if I do a linear combination, will I ever get 1 here? Is there a linear combination that will give me 1 here? Exactly, exactly. So you can do R2 equals R2 plus R1, right? You can do this, right? So is everybody able to see if I do R2 equals R2 plus R1, I'll get a 1 here. But if you do this, R2, if you do R2 equals R2 plus R1, what will happen? The entry that you made 0 also gets disturbed, right? If you make R2 equals R2 plus R1, you're right in saying that this entry will become 1. This entry will become 1. But also, you're making other entry 1, right? But in our RREF, this is not at all okay. It is a strict condition that the entries below the leading diagonal should be 0, and entries on the leading diagonal should be 1. But if you're not able to get a 1, it is okay to leave it as 0. This is a okay condition, but this is a strict condition, right? In pursuit of making this entry 1, you're disturbing a 0 already, 0 that we produced already, right? That is why when you encounter a column, when you encounter an entry that you cannot make it to 1, you'll just leave it as it is, right? This entry cannot be made 1, so this entry you leave it to 1. So you leave it to 0, and you will go to next entry. Now you see next entry is already 0, so this, we are also done here. Then we are also done here, right? Now we'll move ahead to third entry of the third column. So I think all of you I hope it is clear to all of you that why I should not do R2 equals R2 plus R1. Right? Now okay, I think it is clear. So now let's move to third entry of the third column. Can somebody suggest an operation? Anyone? Hmm. Yes, R3 equals R3 minus R1. Right? Again observe, when you do R3 equals R3 minus R1, this entry will become minus 1. Do you see what I mean? This entry will become minus 1. But we don't want that, because this entry, as per our definition of RREF, this entry should be 0 only. Then when you're doing an operation, we better not disturb something that we have already fixed. All right. Is there any other way I can make this one? Oh, we need to make this entry 1, right? On the diagonal it should be 1. So you're saying R3 equals R3 minus 2 times R2, is it? Yeah. Can I suggest a even simpler operation? We saw scalar multiplication, right? Can I simply do R3 equals R3 by 2? Or I'm multiplying a scalar to R3. R3 equals 1 by 2 times R3. Can I do that? So these are the three conditions that we saw, right? One is linear combination, second is permutation, third is scalar multiplication. I can do scalar multiplication, right? So why I'm saying that, anytime you find a entry that you want to make it 1, you can blindly follow this rule. If that entry is not 0, you can always make it into a 1 by multiplying that entire row with a reciprocal of that entry, right? Now let me follow that. Let me follow that, like blind rule, and make R3 equals R3 by 2. What will happen if I make R3 equals R3 by 2? Here I will get a 1. Here I will get a 1. This will become 3 by 2. So 3 by 2, and this will become 1 again. Okay. So now I'm done with third entry of third column. I should go to this entry, and I want to make it 0. Can you suggest an operation that will make this 0? R3, exactly. R4 equals R4 minus R3. And when you do that, this entry will become 0. This entry will become 0. 3 minus 3 by 2 will become, um, 3 minus 3 by 2 will become 3 by 2, right? And 6 minus 1 will become 5. Okay. Is it okay? Yes, yes, you can do R4 minus R2. That's a very, very valid operation. And you can do that only because this entry is 0 here. You are fortunate that this entry is 0. Now, what would have happened if this entry were non-zero? Then you will unnecessarily disturb this 0. This 0 will become non-zero again, right? Now, just because the pivot, the second entry of second column happened to be 0, you can also do R4 equals R4 minus some scalar multiplication times R2. That is also perfectly valid. Okay. Now we are done. We came to the last entry. Now can somebody suggest how to make this last entry one? R4 equals, yes, R4 equals 2 by 3 times R4, right? If you do that, then this entry will become 1, this entry will become 1, and this entry will become 10 by 3. This entry will become 10 by 3, right? Now we are done. So I hope the algorithm is clear. How to convert a matrix to a row reduced echelon form. Is it clear? Now, I think I demonstrated two of the three operations. That is, in obtaining RREF, I showed you how to apply linear combination, how to apply scalar multiplication. Let us see when will you apply permutation, right? Now, let me give you, like some arbitrary matrix A. A equals, let's say, 1, 2, 3, 4, 0, 0, 5, 3, 0, 1, 2, 4, 0, 0, 3, 2. Can you suggest this RREF conversion procedure for this matrix? First, what you will do, you look at the first entry of the first column. You will try to make it one. In this case, it is already one, so you will go to the entries below the first entry, entries below this one, right? And you will want to make all such entries to 0. Now, in this matrix, they are already 0, so you are done with first column. Then what you will do, you will go to the second entry of the second column, this entry, and you want to make this entry 1, but this entry is unfortunately 0, right? Now what is the condition? You will try to, you will try your best to make this entry 1. If in case you are not able to make this entry 1, then you will leave it to 0, right? Now here, can you make this entry 1? So while making this entry 1, you should not disturb the other entries that you have already attended. Yeah, what can you do? R2 plus R3. Yes, you can do this, but rather let me suggest simpler operation. Can I permute A? A is in the order, let's say 1, 2, 3, 4, right? And we already saw permutation is also a legal operation. Now, if I write A in the order 1, 3, 2, 4, then what will I get? 1, 0, 0, 0, 2, 1, 0, 0, 3, 2, 5, 3, 4, 4, 3, 2. Now, do you see here already we got a pivot here? Sorry, already we got the second entry 1, and by means of applying this permutation, I get these entries for free, right? We could have also done what you suggested. We could have done R2 equals R2 plus R3. Then what will happen? This entry will be 1. Then I have to come here and I should adjust this entry to 0. Right? There is nothing wrong in doing that. That is all. That will also give you perfectly correct answer. But here I am suggesting, like one other legal operation. We saw that permutation is also a legal operation, right? Yeah. Then so you obtained this. Then you will go to third entry of the third column. You will try to make this one. And here we saw that you will use scalar multiplication to make this one. So you will do R3 equals R3 by 5. That will give you 1 here, and this will become 3 by 5. Then you will try to make R4 0 by multiplying with the third row. So this is one case where R3 equals R. Sorry, if you want to make this entry to 0, you should not do R4 equals R4 minus 3 by 2 R2. You should not do this. Why you should not do this? Because if you apply this equation, this entry will become 0, but this entry will get disturbed, right? A correct operation here will be to multiply R4 equals R4 minus 3 by 5 times R3. Are people able to follow what I mean? What I mean here? You should be careful in terms of selecting the rows when applying linear combination, so that whatever the work you did earlier does not get ruined. Okay? Is there any doubt so far? Yeah. So then I assume that like if I give you any matrix, you will be able to convert it into row reduced echelon form, right? There is no doubt in applying these three operations, right? Or do you want me to quickly revise before we end the session? Okay. So we started with this class with class with how to find, is there an efficient method to find a solution to system of linear equations? Solution to system of linear equations. A system of linear equation is can be written in matrix format in this manner: Ax equal to b. And last class we saw how to take augmented matrix. What we do is to append b to a. That will give me augmented matrix, right? Now it turns out, so in next class we will see how to you exploit RREF to find solution efficiently. But this class, let's only worry about the algorithm or the pseudocode that gives us RREF given a matrix A, right? Now the goal is to convert a comma b to row reduced echelon form. Now what is row reduced echelon form? Given any arbitrary matrix b, let a comma b, let's say it's a square matrix or a rectangular matrix, it doesn't matter. What you will do is to draw the leading diagonal. Now you will try to make the entries along the leading diagonal equal to 1. You will try to make that. In case you are not able to make this entry 1, it's okay to leave some of these entries as zeros, right? But if you can make 1, you should definitely make 1, right? That is the condition on the leading diagonal. Next condition is the entries below the leading diagonal should be 0, and the entries above the leading diagonal can be anything that we don't care. This is the structure of row reduced echelon form. Next, we saw how to convert this matrix to row reduced echelon form. Now, for that, we need to come up with some set of legal operations, right? Now, these legal operations should be inspired from whatever you do to solve system of equations in a paper. If I give you a paper and give you, let's say, three equations with three unknowns, what all will you do to obtain the solution x? These operations should be inspired from that the operations that you apply in paper, right? And we saw that you predominantly or you only apply three such operations. So these three operations are called as elementary row operations. Elementary row operations. Now what are those operations? First we saw linear combination. What is a linear combination? It is an operation of the form Ri equals Ri plus alpha times Rj. Now mind you, I told that you should always represent linear combination in plus alpha times Rj format only, right? While it is perfectly legal to write Ri equals alpha times Ri plus Rj, this is also a valid operation. But in this class, we'll restrict to operations of only this type. And this time, these are correct. There's nothing wrong. But we'll try to avoid this kind of operation. Why will we avoid? Because later we'll see something called LU decomposition. LU decomposition. Now, if you obtain RREF following only such operations, then LU decomposition is straightforward, right? That is why I restrict to equations of the form Ri plus alpha times Rj. Okay. Then second operation that we saw was permutation. What is permutation? Now given matrix A x equal to B, or the matrix augmented matrix AB, right? You can interchange the rows of the matrix in any which way you want. You can interchange the rows, right? And one more thing I told you, in Ax equal to B, you should not interchange the rows of X. Do not interchange the rows of X. And we saw why we should not interchange, right? So we saw if you interchange, the solution gets swapped. Meaning earlier x2 was equal to 2. After you interchange, x1 will become equal to 2, and we don't want that, right? In permutation, you will only permute the rows of A and rows of B in the same order. What do I mean by same order? Let's say you swap rows 2 and 1, then you swap the same rows in B also. Okay, this is a permutation operation. Then at last we had scalar multiplication. What is scalar multiplication? Ri equals alpha times Ri, and alpha should not be equal to 0. Okay, now given a matrix, you will apply one or many of these operations in a sequence to obtain a matrix in this structure, right? Now what is the pseudocode for a procedure you will follow? Now given a matrix, first you will visit first entry of first column. So even before that, let us draw the diagonal. Let us draw the diagonal. Let's assume diagonal ends here. Then what you will do, you will visit the first entry in this diagonal, right? You will try to make this entry 1. Now if this entry is non-zero, let's assume you had a 2 or 3 here, you can readily apply scalar multiplication, right? To make the entries on the leading diagonal 1, I can apply scalar multiplication. Let's say this entry is some beta. This entry is beta. You can multiply r1 equals 1 by beta times r1 if beta is not equal to 0, right? If beta is equal to 0, you will try to permute some rows to make this entry non-zero. Once this entry is non-zero, you can make it equal to 1, right? So what I'm saying is, if I entry on the leading diagonal, for instance, if the entry beta, if beta is equal to 0, you will try to permute rows. Okay. Now first you will try to make this entry equal to 1. Once you have made this entry 1, you will try to make all the entries below the this below this beta 2 equal to 0. Now how will you make this entry 0? You will use some linear combination. Now one thing you should be careful when applying linear combination is, you should not you should not disturb, you should never disturb the adjusted entries. That is a thumb rule you should follow, right? You should never disturb adjusted entries, right? What do you mean by adjusted entries? Let's say you are in this entry. When you came to this entry, you have made sure that entries above this entry, entries on the leading line above this entry are equal to 1 or 0, and you have made sure that this part of the matrix is all 0, right? When you apply some operation to make this entry 1, or let's say to make this entry 0, to make this entry 0, in applying linear combination, scalar multiplication, or permutation, any which operation you apply, the work that you have done is basically this part. This part you have adjusted. When you came to adjust this entry, this part you have already adjusted, and this part you have already adjusted, right? You should not disturb the entries that are already adjusted. Okay, you will keep this as a constraint in adjusting entries, right? Now in this manner, what you will do, you will use the three operations sequentially, and obtain a matrix where diagonal is either 1 or 0, and the elements below the diagonal are all zeros. That will give you row reduced echelon format. In next class, we will see how to use RREF to obtain solution to X. Is it okay? Is there any doubt so far? Yeah. Okay. We'll conclude the class. So before next class, I request you to take at least two problems and convert that problem into RREF yourself. Right? Friday 6 to 7 p.m. Yeah. So in fact, it will be better for you if you take a matrix and apply the steps that we discussed today to convert it into RREF right now. Yeah. So then I think with the next class we'll be done with solution to system of linear equations. After next class we'll see LU decomposition. Okay. So this will cover at least 40% of linear algebra in gate. After LU decomposition, we'll start with eigenvalues, eigenvectors, and those stuff. Okay. Yes. Yes. Oh. Okay. Mhm. For GATE Computer Science, I am the only TA available. So uh, I think my commitment to this is for a semester, and I meet once in a week, every Friday 6 to 7 p.m. and discuss linear algebra. So while I meet, I'll try to cover the entire syllabus of linear algebra for GATE. Okay. After me, I don't know if somebody else will follow. That I'm not very sure. Yeah. Okay then. Thank you so much. Yeah. Bye.